Okay, so now basically about the parabola, what we want to do here right now is that we want to basically first define what a parabola is. So in the previous videos we talked about circles, and we said that basically the circle was the locus of all points that are at a or basically I would say that the locus of all points that are at a fixed distance from a point in the plane, and that point was basically, suppose that for example you have a circle over here, so a circle basically is the locus of all points that are at a fixed distance from a fixed point in the plane. That point is called the center of the circle, and that fixed distance is called the radius of the circle, usually denoted by r. So that was basically a circle, and that was not that that was basically simple, at least as compared to parabolas. Parabolas are a little bit more complicated because basically the shape of a parabola is fundamentally a little bit more complicated, and so it takes more of a definition to define a parabola, or to basically define the equation of a parabola. Meaning that, for example, a parabola is, I don't know why my lines are, meaning that the shape of a parabola is basically something like this, and then that just keeps going in this direction, this way, and then you have this point over here, and you have some other point over here, and you have some line over here. Now, of course, this point and this line over here, this line is called the directrix of the parabola. It's a line. And this point over here is called the f, or the focus of the parabola. And these two, and this line and this point, is basically, both of these are required. They have to be there so that we can actually we can derive some formula for this conic section. Basically, this seems to have been the best way to do that. There must be, of course, other ways of doing the same thing, but this way basically has stuck in mathematics. Meaning that they say that if you have, for example, your focus over here, this point over here, and this has some definition, and a line called the directrix over here, and this has some definition as well, then in that case, and the definition of this focus is that basically, if you take this as the origin 0, 0, then this point is at a, 0, and this line, the equation of this line is x is equal to a, for example, and this is negative a, 0, of course. I'm sorry, this is basically, yeah, of course, this is a, 0, and then this line is x is equal to negative a. So if you have a line at x is equal to a, and then you have some point at a, 0 on the x-axis, then relative to this point and this line, you can define a conic section called a parabola in such a way that every point that you pick on this parabola is going to be basically like this, meaning that, for example, you have the distance between these 2 points is equal to this perpendicular distance. Again, if you have another point over here, this distance is equal to this perpendicular distance, and so on and so forth. Meaning that, for example, if I take this as P1, if I take this as P2, if I take this as P3, for example, then again this distance is going to be equal to this distance over here. Meaning that, for example, B1 B2 and B3, then you can say that basically FP1 is equal to basically P1B1, or FP2 is equal to P2B2, or FB3, or I'm sorry, FP3 is equal to B3 B2, I'm sorry, P3, this looks like, then you can say that again FP3, for example, FP3 is equal to P3B2, for example, P3B2, and so on and so forth. Meaning that you can say F of F basically, I don't know why I ended up with this kind of configuration, B1, B2, B3, B1, B2. This is supposed to be P3. So then you can say that F of B of n is equal to P of n, B of n, basically. B of n. So that means that it simply means that any point that you pick on this parabola, the distance of that point with the focus over here is equal to the perpendicular distance of that point from the directrix. That's basically all that it means. So that is the definition of a parabola. And because of this complexity, then of course deriving the formula related to a parabola is a little bit more complicated than a circle, but it's not that complicated. We can of course define it pretty easily. There is no problem with that. Now, as a definition, what you can say is that a parabola is the set of all points in a plane that are equidistant from a fixed line, that are equidistant from a fixed line, and a fixed point, and this is line and a fixed point, and a fixed point not on the line, in the plane. So this is the definition of a parabola. That a parabola is the set of all points in a plane that are equidistant from a fixed line, which is called the directrix, and a fixed point excuse me, and a fixed point not on the line in the plane. That is basically what a parabola is. And so the fixed line is called the directrix of the parabola, and the fixed point is called the focus of the parabola. And there is something interesting about parabolas, and that is basically that parabola, you can basically take this word apart as para and bola. So para seems to mean 4. In English it means it could be translated as 4, and bola seems to mean throwing. Mean throwing, I'm sorry. And it seems that they have given this conic section this name, parabola, because it seems to have the shape of basically when you throw a ball in the air, meaning that the ball goes up in the air and then comes down like that. So that means that throwing a ball up in the air. So that seems to be the reason why they have given the parabola the name parabola. And so that is that. And of course here we said that this point is not supposed to be on this line. And if the point is on this line, then basically what happens is that, for example, you have your coordinate axis here, and you have, for example, let's say that you have some line over here, take it as directrix, and if this point is on this line, then the set of all points that are equidistant from this point and this line is going to be basically a straight line perpendicular to the directrix, meaning that it's going to be a straight line, because, for example, you take this point over here, which is on this line, it is at distance 0 from this line, and well, again, the distance 0 from the point itself. And then again, for example, you can take this point over here, it is at this distance from the line, the perpendicular distance, and the same distance from the point. Take this distance over here, it is at this distance from the point and also the same distance from the line, and so eventually you will get a straight line like this. Now we call this case of a parabola if the focus is on the directrix, and as a result, of course, we will get a straight line, not a curve like that. This case we call it the degenerate case of a parabola. Degenerate case of a parabola. We call this case the degenerate case of a parabola. Okay, so that's basically that. Okay, so now there is something else which is related to these parabolas, which is called the axis of the parabola. And that is, if you have, let's say that this is the y-axis and this is the x-axis, and let's say that this is your directrix, let's call it L, for example, and let's say that this is your F with coordinates, for example, coordinates a comma 0, and let's say that this is the origin and your parabola is some parabola like this. So if that is the case, then basically a line through the focus and perpendicular to the directrix, which is basically essentially the x-axis in this case, is called the axis of the parabola. So this is the x-axis in this particular case is called the axis of the parabola. So this is the axis of the parabola. This point over here is called the focus of the parabola. This line over here is called the directrix of the parabola, and this point over here is called the vertex of the parabola. And this over here, this basically this conic section over here is the parabola itself. So now that basically we know enough about these definitions and basically all the different parts and different things about parabolas, now we can basically find the standard equation. Find the standard equation of a parabola. So in order to do that, so basically based on what we said over here, we could have basically four different basically arrangements or configurations or ways of representing a parabola in the in an xy plane, meaning that your parabola, or basically meaning four ways that your parabola could actually what do you call it? It could look like, I mean, it could have four different directions. That's the best way that I can describe it for now. Meaning that your parabola could be, for example, something like this, and this would be your directrix, this would be your f, and then basically the coordinates of this point would be f, basically a comma 0. The equation of this line would be x is equal to negative a, and this would be the y-axis, and this would be the x-axis. So this would be one way that you could represent a parabola in the xy plane. Another way that we can have a parabola is that if this is the x-axis and if this is the y-axis, it could be the other way around, meaning that you could have your parabola in this orientation, and in that case your f would be over here, your directrix would be over here, and the coordinates of this point would be negative a comma 0. The equation of this line would be x is equal to a, and you need to pay attention to the signs over here. So this is negative a, this is positive a, this is positive a, negative a, and that's basically another way of representing a parabola. Another way that there is to represent a parabola is that either it could be basically upwards, opening upwards, or opening downwards, meaning that you could have, for example, something like this. You could have basically your y-axis and x-axis over here. Your parabola could basically open upwards, like this, and then you would have your f over here, the directrix would be over here, this would be your L, and that the equation of the directrix would be L is basically y is equal to negative b, or negative a, you could say as well, could be negative a, and your f, the coordinates of f would be basically 0 comma a, or your parabola could be in this configuration over here, which is opening downwards like this, and then you would have your directrix over here. This would be your x-axis, your y-axis, and this line over here would be y is equal to positive a, and your focus would be basically 0 comma negative a over here. And depending on which configuration you have, you will have basically mainly two different variations of the equations for these parabolas. So if your parabolas are either basically opening to the right or towards the right or towards the left, your equation is going to be basically y squared is equal to 4 times ax. Now if your parabola is opening towards the right, then it's going to be y squared is equal to 4 times ax, positive 4 times ax. If it's opening towards the left, then your parabola is going to be y squared is equal to negative 4ax. So these are basically the two different ways that you can represent the parabola algebraically if the parabola is opening towards the right or towards the left. Now when it comes to these two configurations, the equation changes a little bit, and in this case you have x squared instead of y squared, you have x squared is equal to 4ay. So over here we had y squared is equal to 4ax. Here over here we have x squared is equal to 4ay. So now in this case, if the parabola is opening towards the top or upwards, your equation is going to be equal to x squared is equal to positive 4ay. If your parabola is opening towards the bottom of the coordinate axis or the coordinate system, then your equation is going to be x squared is equal to negative 4ay. Negative 4ay. And that's basically the four different configurations, or basically you could say two different configurations that you have. So what that means is that if the axis of the parabola is either well, since we are not talking about parabolas basically shifted around, for example, we are not talking about this parabola over here. Of course, you could have a parabola, for example, with the axis over here, something like this, and even shifted to the right a little bit. The vertex could be over here. You could even have a parabola, for example, in this configuration. In this configuration, this could be the axis, and your parabola could be basically something like this. You could have a parabola in this configuration, something like this, and you could have any other sort of configuration for parabolas. And we are not okay, so since we are not talking about these cases over here, we can very simply restrict our discussion to basically parabolas. So we can very easily basically restrict our discussion to parabolas that are basically either in this configuration or this configuration or this one or this one. And so you can say that basically we have these two forms of equations, and then the coefficient of ax is going to be either positive or negative in each case, or the coefficient of ay is going to be positive or negative. Anyway, now let's go. What we want to do here now is that basically the first configuration that we drew over here was basically this configuration, which is basically, let's say that you have a parabola over here where you have your focus over here f with coordinates a comma 0, and you have your directrix over here, this line. Let's say that this is L, which with equation x is equal to negative a. All right, so then if I assume that F is the focus and L is the directrix here, and if Fm is perpendicular to the directrix, and basically Fm perpendicular to directrix, and you know that basically O is the midpoint of Fm because F is at is basically at the distance 0, a, 0 on the x-axis, and this line is the equation of this line is x is equal to -8. That means that this distance is a. The distance is a. Of course, the equation becomes x is equal to -a because we are going in this direction. But anyway, this distance is a, and this distance on the x-axis is also a. So that means that OM is equal to OF. OM is equal to OF. Okay, so now you can basically pick any point on the parabola, for example P, with coordinates x, y, and by the definition of the parabola, we said that the distance between point P and this point F, which is the focus of the parabola, this distance is equal to the perpendicular distance of point P from the directrix. And I can call this point, I can call it B with, for example, with the coordinates -a and, well, some y, for example, over here. Now so basically I know that PF is equal to PB. Now, if you use the distance formula, AB is equal to the square root of x2 minus x1 whole squared plus y2 minus y1 whole squared. If you use this formula for these two distances, what you will get is that PF, which is basically, you have 2 points over here, PF, you have the point basically x, y, and you have basically a, 0. So then you can write this distance as the square root of, for example, x minus a whole squared plus y squared. Now PB you can write it as, so P is basically x, y, and B is -a, y. So then PB is equal to the square root of I can take it as x minus -a, which is x plus a whole squared, plus y minus y whole squared, which would be equal to the square root of x plus a whole squared, the square root of that. So that is your PB. So now if PF is equal to PB, since PF is equal to PB, then you can write basically the square root of x minus a whole squared plus y squared is equal to the square root of basically x plus a whole squared. And if I raise both sides of this equation to the second power, I'll get x minus a whole squared plus y squared is equal to x plus a whole squared, which means that basically x squared plus a squared -2ax plus y squared is equal to x squared plus a squared plus 2ax. Now x squared, a squared, x squared, a squared, so that means that then basically y squared is equal to 2ax plus 2ax. That means that y squared is equal to 4 times ax. y is equal to 4 times ax, and of course over here a is greater than 0, as over here a is greater than 0. I mean by this construction we agreed on the fact that a is greater than 0. You need to be careful about that because we are going to use it. Because we took this direction on the x-axis as a. That means that a is a positive value. Otherwise, we could have taken a as a negative value, or we could have defined a as either being negative or positive. But we explicitly said that a was supposed to be a positive value. So what that means is that now, if I write, so basically the equation that we got was basically y squared is equal to 4 times ax, a greater than 0, and this is the equation of the equation of the parabola with basically with vertex at 0, 0 with vertex at 0, 0 and focus at a, 0 and directrix at basically directrix as I would say directrix as x is equal to negative a. And of course, as I mentioned before, a is greater than 0. So that means that I can say hence any point on the parabola satisfies this equation. I call it, for example, equation number 1. Satisfies equation number 1. Now there is one, I mean, you can of course show the converse of this as well, meaning that you can say that conversely, if p with the coordinates x comma y satisfies this equation number 1, if p basically satisfies this equation, meaning that if p is actually on this parabola, then we said that pf was basically, if you the configuration or basically this was my parabola over here, this was my directrix at x is equal to negative a, and this was basically f with coordinates basically a comma 0, and this was the y-axis, and this was the x-axis. Now p was some point over here, for example x comma y, and this distance over here pf, if you calculate pf over here, pf is going to be using the distance formula. You can write x minus a whole squared plus y minus 0 whole squared, which is equal to the square root of x minus a whole squared plus y squared. So PF is going to be equal to this, of course. Now if this point, if basically px comma y satisfies this equation number 1, which was up here, if it satisfies this equation, that means that means that you, instead of y squared over here, you can simply write 4ax. I hope that you understand that the logic that I'm using here. What I'm saying is that if px comma y satisfies this equation, that means that it is, for example, let's say that I have some equation y is equal to x. So that I have some equation y is equal to x. So then I have some point over here. For example, 1 comma 1. Now what I can say is that if 1 comma 1, and if I call this equation number 1, for example, if 1 comma 1 satisfies equation number 1, if this satisfies equation number 1, which it does, then I can say, for example, then suppose that, for example, I have some equation over here, some expression over here, the square root of, for example, y minus x plus a, for example, something like this. So from this, basically I know that I know that y minus x is equal to 0, right? So then I can simply, instead of the square root of y minus x plus a, if I do need to, I can write basically 0 plus a, because y minus x is equal to 0, and that's equal to the square root of a. So I'm using the same logic over here, and of course you can see this over here, meaning that why this actually works is that if y minus x is equal to 0, then, for example, suppose that you have the square root of y minus x plus a. So let's just call this, for example, plus 4. And what that means is that basically then if I write this expression, what this expression means is that you have the square root of y minus x plus 4. But over here I know that y minus x is equal to 0, and of course here I should say basically x and y, for example, x and y. Now here I can say that if x and y satisfies this equation, very simply I can basically substitute x minus y as 0 over here, and I can write it as 0 plus 4 is equal to the square root of 4, which is equal to 2. Now why this works is that if I write this equation as the square root of y minus x plus 4, then of course if I set this equal to, for example, some value, for example a, for example, then I can write a squared is equal to y minus x plus 4, and since y minus x is equal to 0, since y minus x over here is equal to 0, I can write a squared is equal to 0 plus 4. So a squared is equal to 4. So a is equal to, well, plus or minus 2, but I'm ignoring the negative side, so a is equal to 2. That is what I've done over here. So I can use the same logic over there to basically to prove the converse of what we found over here. What we found over here was that if basically if you have some point with coordinates x and y having this relationship with this line and this relationship with this point f over here, then the equation of all such points in the xy plane was going to be equal to y squared is equal to 4ax. That's what we found over here. Now the converse of that would be if this point p x comma y satisfies this equation, it is going to be on that parabola that we talked about. Okay, so that's what we want to do. So now what I can say is that if p x comma y satisfies this equation number 1, so then I can simply calculate pf over here, which is x minus a whole squared plus y squared, and over here y squared is equal to 4ax. So over here I can write the square root of x minus a whole squared plus 4ax plus 4ax, and what that means is that then this is equal to the square root of x squared plus a squared minus 2x plus 4ax, and that is equal to the square root of x squared plus a squared plus 2 times ax, and that is equal to the square root of x plus a whole squared. That is equal to x plus a whole squared. Now p, basically this distance over here, if I call it pb, for example, this point, if I call it b with coordinates, for example, negative a comma y, if I calculate this distance over here, is going to be equal to the square root of, so the points are basically x comma y and negative a comma y. So to find the distance between these 2 points, which are essentially p and b over here, you can write x2 minus x1, so x plus a whole squared plus y minus y whole squared, which is equal to the square root of x plus a whole squared plus, well, 0 squared, which is equal to 0. And so you can see that pf, and this is basically pb, so x plus a whole squared is equal to pb. So that means that if px and x comma y satisfies, so what that means is that if px comma y satisfies this equation, y squared is equal to 4ax, a greater than 0, then pf is equal to pb. Pf is equal to pb. What that means is that pf is equal to pb. That means that if this point satisfies this equation, then you can conclude that pf is equal to pb. That means that basically the point is actually on the parabola. And so what that means is that if you find any point on the plane that satisfies the equation of the parabola, that point is actually going to be on the parabola. That's basically what that means. Okay, so that is basically the whole story here. So now basically to basically to sum it up, what we have done here, basically we said we have proved that the equation of the parabola, the equation of the parabola with vertex at the origin, the focus at a comma 0, and the directrix as x is equal to negative a is basically y is equal to y squared is equal to positive 4ax. That's basically what we did so far. Now, as an important point as something important to point out here, basically in this equation we said that we had y squared is equal to 4ax, and we said that a is greater than 0. Now, since a is greater than 0, then what that means is that, of course, y squared has to be a positive value. Because this is the square of some number, it doesn't matter whether y is negative or positive, but then y squared has to be positive. And since a is positive, then x can only be positive. It can be positive or 0, depending on the value of y. But it cannot be a negative value, because if x is a negative value, then this whole part over here becomes negative, and this cannot be negative. So that means that x can take on only positive values or 0, but no negative values. And then that's basically the whole story here. So then basically when you have this sort of configuration, then you have a parabola like this, whose vertex is at the origin, and it extends indefinitely towards the positive axis, and it just keeps on going in the first quadrant and in the fourth quadrant over here. It's just basically this parabola that you have. Now this equation that we found over here, y squared is equal to 4ax, this equation, along with the other equations that we found. For example, if your parabola looks like this, it's going to be y squared is equal to negative 4ax. If your parabola is basically something like this, it's going to be x squared is equal to 4ay. If your parabola is like this, it's going to be x squared is equal to negative 4ay. All of these four equations over here are called basically the standard equations of parabolas. Standard equations of parabolas. And that is that. Now there are a few points over here that we can point out here, and then we are done with this part. There is only a little bit more theory over here, something called about the Latus rectum, but that's not very, I mean, that would take only a few minutes to explain. Now there are basically a few things that you can observe here. There are a few things that you can observe here. So basically, the parabola is symmetric with respect to the axis of the parabola, meaning that, of course, you know that if you have a parabola over here, and if this is let's say the x-axis is the axis of the parabola, then your parabola is going to be symmetric with respect to the axis. So over here, your axis basically is this x-axis over here, and of course your parabola is symmetric with respect to your axis, meaning that if you take any point over here, the perpendicular distance of this point to the x-axis, and if you take the same distance, the same perpendicular distance to the other side, this point is also going to be on the parabola, meaning that, of course, I should have drawn the parabola something like this. Or if you take this point over here, come this distance down, and the same distance down, this point is also going to be on the parabola, and so on and so forth. That means that the parabola is symmetric with respect to the axis of the parabola. Now, over here, basically the equation of this parabola that we found, basically we had 4 equations over here. We had 4 equations over here. So we had these parabolas over here. So suppose that you have this parabola over here. And we found that the equation of this parabola was y squared is equal to a 4 times ax. This parabola over here, we said that the equation was y squared is equal to negative 4ax. This parabola over here, we said that the equation is basically x squared is equal to 4 times ay. And sorry, I messed something up. And basically this parabola over here, we said that the equation was x squared is equal to negative 4ay. So as you can see, if the axis of the symmetry of the parabola is along the x-axis, then you will have y squared terms in the equation of the parabola. If the axis of the symmetry of the parabola is along the y-axis, then in that case you have x squared terms in the equation of the parabola. So, and of course, if you have x squared terms, the axis of symmetry is along the y-axis, and if you have y squared term, the axis of the symmetry is along the x-axis. So that's basically one thing. Now, when the axis of the symmetry is along the x-axis, when the axis of symmetry is along the x-axis, as you can see in these 2 cases over here, then the parabola opens towards the right if the coefficient of x is positive. If the coefficient of x is positive, and it opens towards the left, if if the coefficient of x is negative. Okay, so now there is actually two basically there are basically two more cases over here, which is basically if the axis of the symmetry is along the y-axis, if the axis of symmetry is along the y-axis, then the parabola opens basically upwards if the coefficient of y is positive, and it opens downwards as you can see here, if the coefficient of y is negative. So very simple, very logical. There is nothing complicated about that. There is this little thing left here that we need to discuss, and that is called the has a weird name, Latus Rectum. It is called the Latus Rectum of the parabola. Latus Rectum. It's supposed to be some Latin name or something. So the Latus Rectum. So the Latus Rectum of a parabola is a line segment. So suppose that you have this parabola over here, and it opens towards the right, and this is your focus, and this is your directrix. So you have y over here, you have x over here. The Latus Rectum of your parabola is a line segment perpendicular to the axis of symmetry, to the axis of the parabola, meaning this line segment over here, and this is the axis of the parabola. Over here you have the axis through the focus whose endpoints lie on the parabola. So it has a very neat and clean definition. So we can say that the Latus Rectum of a parabola is a line segment, not a line but a line segment, meaning that the line is actually terminated at these 2 points. Is a line segment perpendicular to the axis of the parabola through the focus whose endpoints lie on the parabola. That is called the Latus Rectum of the parabola. Now this Latus Rectum has some length. The length of the Latus Rectum So in order to find the length of the Latus rectum, you already know that the so there is a good way to find the length of the Latus rectum, and that is basically, you know that this is the midpoint of these 2 points, and you know that this length is A. Okay, so if I take this point as, for example, I take this point as A, for example, I take this point as, for example, C, and I take this point as B. And I know that basically AF, this point, if I take it as F, by definition, I know that AF is equal to AC. AF is equal to AC by definition. By definition, these two lengths are the same. And since AB is equal to 2 times AF, since AB is equal to 2 times AF, and AB is equal to 2 times AF because well, you know that your parabola is symmetric about the axis, so that means that whatever length you have over here, you have the same length on the other side. That means that AF is equal to AB, meaning that AF is equal to AB. So since AB is equal to 2 times AF, then that means that AF is equal to AB. That means that AF is equal to 1/2 AB. 1/2 AB, or of course that's not a good way to write this. So you know that the length AC over here is actually this length over here, since the coordinates of F are basically, for example, let's say the coordinates of F are basically A, 0, and the coordinates, and the equation of this line is x is equal to -a, then the length of AC becomes basically A units over here and A units over here. That's 2A units. That's 2A units. So what that means is that I can write this equation as AF is equal to 2A, and since AF is equal to half of AB, that means that AB is equal to 2 times AF. AB is equal to 2 times AF. So what that means is that what I want to find is AB over here, and I can find AB in terms of, so instead of AF I can write basically 1/2 of, so this means that basically AF is equal to 1/2 of AB. 1/2 of AB. So instead of AF over here I can write 1/2 of AB is equal to 2A. That means that AB is equal to basically 4A. And that is the length of the Latus rectum of a parabola. I'm writing the Latus rectum of a parabola, and I'm assuming that, for example, the Latus rectum might be used for other conic sections or other configurations or other things like that. But and the same sort of expression has been used over here in the text, so I can safely write this as the lattice rectum of the parabola. So that's basically all the theory that we need so far about these parabolas, and we have we have some examples over here that we will go through, and then we have some exercises as well. So, but the rest we will do in the next video. See you in the next video. Thank you.